All righty. Full screen. I think I got everything centered here. We're all set to go. Lesson set 17, which is actually a test. And I'm doing the graphs first, which are problems 60 through 70. And I'm doing so because I really believe that little looks at every problem 4 days in a row, usually you get some understanding. But if you're working sequentially and you continue to work sequentially through the lesson set, nothing wrong with that as long as you finish the lesson set. But if you're having success with the first 20 or 30 problems, and by now you should, because it's the 17th time you've seen the same material, you should be able to get some neuronal activity connected, some smooth pathways to be able to do some computations. Then you might not be looking at the last problems enough for that to happen there. So we're starting with problem 60, going to 70, and let's have at it. So the first question, problem 60 is graph -2, absolute value x -4 -6. What do you need to know about absolute value? It measures distance from x equals 0 on a number line. The x-axis, how far are you from 0? You can think of it that way. And so 0 is a minimum, right? Because distance is always positive. So what makes x -4 equal the absolute value? What makes the absolute value of x -4 act like the absolute value of 0? 4. And if distances are always positive, multiplying by a negative is going to get us a maximum. And what do you do with x values? You use them. So if you put 4 in, you get 0 times -2 is 0. You get -6, and hopefully you can look at that and say, wow, I think I can get that quickly. Now, I like the y-intercept, so I'm going to plug a 0 in. You're going to cut, if a graph's going to cut through the y-axis, should go through at the correct location. So 0 -4, the absolute value of 4, 4, -8, -6, -14. Which implies that 0, 4, 8 also gets me -14. And a quick check of your x's divided by 2 should give us the critical number inside the absolute value, which is 4. Now, other places on the test, if I follow my finger from left to right, I'm going up. So this side is 4 times, -2 becomes +2 times parentheses x -4 -6 when x's are less than 4. And I'm going down -4 times x, I did it again, -2 times x -4 -6 for x's that are, got my eraser here, for x's that are less than or equal to, greater than or equal to 4. I got to start actually think about what I'm looking at rather than just talking mindlessly. So there you go. That's how you sketch that, and that's how you can work with that equation. You can work with the branches. 5e to the x -1 plus 7. Yesterday we talked about what are the steps in graphing. Well, the first thing is putting down the shape. This is exponential growth. E approximately 2.71. And if I keep multiplying 2.71 times 2.71 times 2.71, my numbers are growing exponentially. But I'm not just going to multiply by 2.71. I actually have an initial value of 5. Okay, so what makes e to the 0 equals 1 and e to the 1.1 equals 3 is all you need to know to be able to graph an e to the x function, e to the positive x function. There's going to be a ratio of 1 to 3. This is going to be, whatever this number is, this is going to be 3 times that number. And I'm telling you, you're always going to get the first jump being 5. It's going to be there. If you make this thing 0, e to the 0 is 1, you get a jump of 5 on top of 7. 7 is the constant. The asymptotic behavior is over on this side. So numbers like, well, I won't ad lib here. 7 plus 5 gets us 12. If we pick something that mimics this, well, I hope you say 1. 1 minus 1, 0, e to the 0, 1, 5 plus 7, 12. Then we want to make x minus 1 equal 1.1 because then we're going to multiply 5 times 3 and we're going to get a jump of 15. Each and every time this process can occur if you pick those two numbers. So why not standardize it? Why not make it a 3 to 1? Some people prefer 2 to 1. If you prefer 2 to 1, then you're not picking 1.1, you're picking 0.7. I just like working with 1.1 more than 0.7. All right, so 15 and 7 gets us 20 approximately. Now that's approximate. All right, and what x do I want to get 1.1? Back to this one. Well, I hope you can do that in your head here and say 2.1. So that's another location on the curve. And now we have a feel for trajectory. Next one. Okay, so we're sketching. What we now know is a quadratic that has a cup shape up. Get this shape before anything else. And now we look at decreasing areas, 9, 4, 1, 9, 4, 1, decreasing areas to 0. There's a minimum at 0. And then the areas go back up again. Hopefully that trajectory makes more sense than it did 3 or 4 weeks ago. So how do we get this x value? Memorization, minus b over 2a. That's evening off the sides of a rectangle. That's evening off these sides. So if I had x times, I'm just going to take an x out, 4x minus 16, I think we can see that this is 16 units shorter, actually. It's actually shorter than that. So I said, it's okay. Divide it by 2 and you get 8. All right, and 8, I mean, if I put this in factored form, 4 times x minus 2, we have a critical number of 2, a critical number of 0. Not explaining this well, so I'm just going to continue on. You can look at completing the square. There's a better explanation there. Let's just do minus b over 2a, 16 over 8. Well, there's 2 units. 2 units of change. Just double check it. 16 divided by 8, 2. And I wish we had something that could find us our y values if x was 2. Oh yeah, we have an equation to find y values. So we have 4 times 2 squared minus 16 times 2 plus 5. We can always check to see if I came prepared. I got a better marker here. So this is 16 minus 32 plus 5. I like that. I've seen that a lot recently. So minus 16 plus 5 is minus 11. And I like the y-intercept because if you're going to cross through the y-axis, you might as well go through the right place. And it's been given to you anyway. So 0 gets you 5, then 4 gets you 5. You can see the symmetry. Now, what's the graphing form? Because that's also on the test, different places. Well, now that we have this, we know that 4 is the a term. That's going to get me 4x squared minus 2. 2 minus 2 gets us our minimum area, 0 squared. And that minimum area is minus 11. Minimum value, that's what I'm looking for on that question. I'm not looking for the coordinate. I want the y value. And pretty soon I'll be taking points off your test if you don't just write negative 11 for the minimum. What do you have for roots? Roots are real. I hit a height of 0 here. All right, and I can see what I have to do. 2 plus minus the square root of 11 fourths, which is the same as 2 plus or minus the square of 11 over 2. Those are your roots. I hope you can see what we worked on yesterday. Subtracting 11, addition 11 on the other side. 4, multiplication, division on the other side. Squaring, plus minus square rooting on the other side. Subtraction of 2, addition of 2. And that's what I wrote for roots. Just another topic that we're covering. Looks like I'm running out of ink on this one. I didn't anticipate that. We'll keep going for a while. All right. These are the 3 things you need to know when you have a base other than E. Okay? Doesn't matter what the base is. The parentheses has to be positive or it's undefined. And there are a lot of numbers close to 0, like 0.01 1. And that's where you get your asymptotic behavior. So I can use numbers bigger than 4. So I will show that to the reader with a line of demarcation. I cannot use the negative numbers here. I cannot use numbers less than 4. A number like 1, 1 minus 4, -3. I can't believe I'm out of ink already. Oh, I got another marker here. Let's hope. Oh, it's a good one. All right. So I got to pick numbers bigger than 4. Well, I know log base b of 1 is 0. Why? Because b to the 0 is 1. So what do I put on top of b to get 1? That exponent. And logs are values of exponents. So what makes the number 1? 5. And I knew base 3 is going to look like this. Okay. So if I put a 5 in, I get 0. That's great because I'm multiplying it times 2. I don't even have to look at that anymore. If I make a 1, I'm getting a 1 in this case. Sorry, I put the same number down. I hate the same number even in the same conversation. I hear you up there. Thank you. Somebody's giving a test. The desk's around. All right, so log base b of b. Yes, you can see that equals 1. I like the number 1. My God. I like the number 1. You can multiply it by lots of things easily. So what makes the number 3 here? 7. 7 minus 4, 3. What do you put on top of a 3 to get a 3? 1. 2 plus 1 is also 3. So there we have a 7 gets us 3. And I'll be giving you these pictures and hoping you can come back and write the equation. If you can go from the equation to the picture, your brain should be able to retrace its thought process. Give me the equation. That's when we name that tune. Maybe we ought to do that real quick, since this won't be all that long. Well, wait a minute, I got my eraser here. I came prepared. Let's create this. Well, okay, what do you see? I hope you see a y value of 1. How do you get to 3? I think you add 2. It's a logarithm with an asymptote of x equals 4. So I write x minus 4. I use the first number. 5 minus 4 is 1. Okay, well, that works. I don't have to do anything. Let's use the second number. 7 minus 4 is 3. So why don't I make the base 3? I think we're back where we started from. All right, let's get this desk out of the way. Okay, so walk the classroom like you walk the field when you're a coach and make sure everything's set up for a practice, because this is a practice session. Next time I'll walk the field. All right, so I see an exponential function. I see one of these growth functions again because that number's bigger than 1. If it was a half, I would have gone in the other direction. All right, so what do we want our exponents to equal? 0 and 1. What makes a 0? 8. Let's put in what we automatically know, minus 4. I've got to jump a 10. 10 units on top of -4 takes me to 6. What makes it 1? 7 times 1 is 7 plus 8, 15. 15, I'm going to be twice as high. So I know that jump is going to get doubled. Yeah, that's pretty good. That looks about 2 to 1. So in here is another point, and I said 15 is going to get me 20 minus 4, 16. How far is it from -4 to 16? 20 units. How far is it from -4 to 6? 10. I hope you can see that that's twice that. And we wouldn't be showing any of that eventually. Eventually, we just know it. But that we do show. Okay, let's keep on moving. Back to a logarithm. What do we want for ln? Slight change from the last log. I want a 0, that's for sure. That happens at x equals 5. I know that ln is is the E notation, basically, base E, and that's bigger than 1. So I have another one of these. I know I want that to equal 1. That happens when I put in a 6, because when I make ln a 1, cancels the multiplication by 4, it's gone, and I get a 7. If you keep seeing that, you get faster and faster and faster. You just make it a 1, you get the constant. And then the next number, if we made it E, we'd get 4 plus 7, but this is where we change. I like the ln of 3, 1.1, gives me numerical field. So what makes a 3 here? What makes 4 ln of 3 plus 7? Because I know that's 4.4 plus 7, 11.4. And I know whatever that distance is, that's going to be 3 times. So I know 11.4. If I just get approximation, I think I got an 8. Yep. Now, what would the inverse of this be? Might as well see the inverse. Switch your x's and your y's and solve for y. But over here, that's going to be an input. So put a number in, subtract 5, ln multiplied by 4, add 7. So I'm going to subtract 7. That's gone. Multiply by 4 becomes division by 4. The inverse of ln is e to the, and subtraction of 5 becomes addition of 5. Let's do that graph real quick, without looking. I believe y equals 5. I'm not even looking at this. I think it's the inverse of vertical 5, horizontal 5. 6, 7, I think is going to become 7, 6. Growth. 11.4, I think 11.4 is going to get us 8. Let's see. Let's put 7 in. 7 minus 7. Oh, e to the 0, 1. 1 plus 5, 6. Wow. 11.4 minus 7, 4.4 divided by 4, 1.1. E to the 1.1, 3 plus 5, 8. Amazing. It works. Okay, we're just starting to get into trigonometry. And we haven't even done the unit circle yet, other than identifying a couple of places. Well, the unit circle is, I haven't drawn one. Unit circle, we take radius of 1. And we start measuring from here. And we walk around the circle. And that becomes our circumference. Right? And whoops, let's get the circumference to match up. Okay, and I start here at 0, 0, 0. Right? Oh, it looks like I got a 7. So I think let's just do the sine function. The sine function 0, 0 goes to a height of 1 to negative 1. And once around the circle, circumference equals 2 pi times radius of 1. That's 6.28 units. 6.28 units gets me back to 0. And I go to a height of 1 and a height of negative 1. That's the range. The range is from negative 1 to 1. Well, what happens if the radius is, we make it 5 times bigger? Let's make it 5 times bigger. Then I think I'm going up to 5 and down to negative 5. And if I add 7 to that, I think I'm going up to 12. And that's not 0 anymore. That's 7. And I think I'm going down 5 to 2. So my range is 2 to 12. And the number in between 2 and 12 is 7. And I go a little trip. And in the first 90 degrees, which happens to be 1.57 radian lengths, which is pi over 2, that's an approximation, right? So one radius length might take me here, 57.3 degrees, and then another 0.57 lands me at a max. And I hope you can see from 0, the first quadrant, there's my first quadrant of triangles, drawing all these triangles, measuring height to hypotenuse, so on and so forth. That's a rendition of what you're looking at. A little messy one at that. Let's keep moving along. We had a conversation. The more conversations you have, the more you start the process. We'll continue those conversations. So here's the relationship. Area y equals 3 times the square root of area plus 7. Well, I got some friendly areas and I have some unfriendly areas. I don't want to take, I don't want to create negative lengths because square roots really are distances. And it's also wreaks havoc with whether something's a function or not, right? That's the inverse of x squared, but we only draw one branch, the principal square root, we call it. And so, what's the smallest? Because I'm not going to work with the negatives, then it starts at 0. Wow. 0 area. Well, there's no square. I can't draw it, but I can represent it. I can represent it as 0 times 0 gets us 0, so it has a square root. So that becomes 0 plus 7. I now can see that 5 gets me 7. And I know I'm going up 3 times faster than whatever the typical square root is, and with a coefficient of 1. So you got friendly numbers. I like this. I like using the square root of 25. So I'm just going to pick 30. And then I've got myself 15 plus 7, 22. Now, let's name that tune. Well, I hope you recognize the square root and say x minus 5 plus 7. And I hope you ask yourself, how do you get from 7 to 22? I think you go up by 15. That's your change in y, right? 7 to 22. And how do you change from 5 to 30? Well, that's a run of 25. Okay, but that's the run right there. That's a run of 25. So when we put 25 in there, does this equal 22? I don't think so. I think 15 plus 7 equals 22. I got to get rid of that. Oh, it's gone now. And what is the square root of 25? It's 5. So, does it look like we got back to what we were looking for? 15 divided by 5 is 3. By God, I hope so. All right. Now, I also showed another square area here, just for fun. 3.01, 9.0601. And wonder what the rate of change is from that square to this square. What's the rate of change? Pause the video and see if you can answer that. Well, we measure rate of change as x2 minus x1 and y2 minus y1. I measure change by how did you get from x1 to x2? I think the brain does that more easily. And how do you get from y1 to y2? That's what I've been doing. But let's do the classic textbook definition of rate of change at a moment. And let's just approximate this. Let's get rid of a bunch of those zeros. Well, how did I change from 3 to 3.001? I hope you say 0.0001. And we changed from 9.006 to 9. That's 0.0006. Wow, that comes out to 6 to 1. And I started with x equals 3. What a coincidence that that's twice that. Nice coincidence. All right, let's move along. Linear function. Why don't we use something we already learned? Minus 2, changed by 4, 2, 6, 10. Minus 7, when I put in a 1, minus 7 gets me minus 6, minus 13, minus 20. Okay, how about we just plot those 2 points? We'll call that 1. Negative 2 is maybe here. Up 1 maybe is right there. We'll call that letter A. What's B? Over 2, down 6. Over 2, down 6 might be here. We'll call that B. Looks to me like we got the equation of a line. Now, based on what we said over on the other wall, 1.57 should jump off at the page at you. There it is, 1.57 radius lengths. And the sign is that height. And I wrote, without looking at Google, 0.999, but I'll check and see if 3 nines appear, because I think we're pretty flat here. I think I'm going to be near 1 for quite a while. But this is just slightly, 1.57 is just slightly smaller. 1.57 than pi, which is 3.1415. Let's get a couple more decimal places divided by 2. So pi is just a little bit to the left, so therefore I'm still in the first quadrant. So I'm saying 0.999. If I all of a sudden went to an 8 here, I'd have to put a minus sign there. One that was horizontal. That kind of looks like a vector. Okay. Anyway, rotator cuff problems. All right, so there's some practice. I hope the camera was centered enough. And I'll do problems 48 to 1 if I can get to it. What time is it? 11. I'll get to it tomorrow. Gonna be running around the rest of the day. All right, everybody be good. Stay warm, as Yasser would say. Stay safe and warm. I like that. All right, ciao.